Hi, and welcome back for the second part of the Service Fabric series. I am Mario Mamalis, and my goal is to share my knowledge of Azure app dev technologies in a fun and interesting way through my channel. In this screencast, I will build upon the theory we covered in the first part. I will go deeper into Service Fabric application development concepts by developing a working application that utilizes several Service Fabric components. If you have not already watched the first screencast of this series, I strongly suggest you do. In the first part, in addition to the theory, I also cover tools, SDKs, and installation instructions for Service Fabric that are not covered here. As always, please do not forget to subscribe by clicking on the button below. Let's take a look at the outline really quick. First, I will explain and demonstrate the working application. Then we will look at the architecture and the different Service Fabric components. After that, I will demonstrate step by step how this application was developed. And finally, we will do a quick recap. So let's get started. Before the demo, let's look at the application details. The goals of this application were to demonstrate Azure Service Fabric services in action, provide some realistic context in order to better grasp the concepts, showcase when and how to use stateful, stateless, and actor services. The application itself is an IoT data capture and visualization system. A device twin is a paraphrase of the coined name digital twin, which refers to a digital replica of a physical device. It is used in Internet of Things systems to provide a visual representation of the state and the dynamics of the physical devices. On our application, the device data are shown on graphic dials using a web app which runs on Azure Service Fabric. The data are saved in stateful and actor services, both unique components to Azure Service Fabric. The data are generated by device simulators, simulating the physical devices running as WPF applications. All services are developed using .NET Core. We're looking at the device telemetry monitor dashboard. This is a web app running on my local development Service Fabric cluster, and you can see that it is empty because we have not activated any devices yet. To activate a device, I will navigate to the folder where the device simulator executable is, and I will run the first instance. There it is, and a few moments later, you will see the device twin appearing on the dashboard, and you can compare the serial number on the simulator and the device ID, and you can see it matching. And now I will modify the values of the temperature and humidity on the simulator, and you can see that the updated values automatically appear on the dials on the device twin. I will start another instance of the device simulator, and as soon as that starts, a new device twin appears on the dashboard with a matching ID. Now, changing the temperature and humidity on this new simulator updates the corresponding device twin. And we can check and see that each simulator updates its own device twin on the dashboard. So we're going to start a new device simulator, and the digital twin appears soon after. And I will play around with the values on all three simulators so that we can see that everything works fine and only the corresponding device twin is changed. So this is the application that we will build together in the rest of the screencast. The dashboard and all of the underlying services are running on Service Fabric, and the simulators are WPF applications communicating to Service Fabric actors. Now let's take a look at a high-level architecture next. The solution follows a rather simple architecture. To the right, we have all the services running in Service Fabric. The dashboard web app is a stateless ASP.NET Core service that we have seen in action in the previous section. It communicates with a device API, which is another stateless ASP.NET Core service exposing HTTP endpoints. The API, in turn, accesses the device registry service. This is a stateful service that is responsible for registering the devices by inserting corresponding rows in a reliable collection, which is the device database for our solution. We have discussed stateful services and reliable collections in the first part of the Service Fabric screencast series. The API also communicates with a device actor service. This is a special type of stateful service. An actor is an isolated, independent unit of compute and state with single-threaded execution. It follows the actor pattern, which is a computational model for concurrent or distributed systems in which a large number of these actors can execute simultaneously and independently of each other. For our purposes, the actors are the device twins. Each device has a corresponding actor in which it stores the current temperature and humidity values. This is a very powerful pattern that works perfectly for IoT systems that can have hundreds of thousands of devices. Service Fabric will seamlessly create and maintain hundreds of thousands of these single-threaded computation units along with their data, achieving high levels of scalability with minimum programming effort. To the left, we have the IoT device simulators. In our system, these are WPF applications that simulate multi-sensor devices that capture temperature and humidity. Without further delays, let's jump right into the code and develop this exciting system. In step 1, we will create the Service Fabric solution and the device registry stateful service. The full solution code can be found on GitHub at this location. I have opened an instance of Visual Studio and I will go ahead and create the Service Fabric solution. In File, New Project, I will select a Service Fabric application, which is under the Cloud category. I will browse to the appropriate location where the solution and all the projects will be located. And then I will name the solution. The name will be Device Twins.Fabric, and that will also be the top level namespace. The first service that we will need to create will be a stateful service, a .NET Core stateful service, and we will name it Device Twins.Fabric.Device Registry. The template executes and we have our Service Fabric solution along with our first service ready to be developed. It's still building. And as a first step, we will update the NuGet packages. And then I will install the Microsoft Service Fabric.services.remoting package, which is needed in order to enable intra-service communication using remoting. Before we start adding functionality, I want to check the local Service Fabric cluster state. To do that, I will start the cluster manager, and this will open up a browser window. And as expected, the cluster does not contain any applications because we have not deployed anything there yet. We can also see that we are running in a one-node cluster in order to speed up development and deployment. The local Service Fabric cluster manager is part of the SDK and tools installations that we covered in detail in the first screencast of this series. The cluster manager is very helpful in visualizing the cluster nodes, applications, configurations, and diagnostic information. I will go ahead and start the application we have in order to deploy to the local Service Fabric cluster and examine the result. We can see that the Service Fabric Explorer now shows one application deployed, which contains one replica and one partition. We can also drill down the application tree and see the application type and name. Let's jump back to Visual Studio and stop the application from running. Okay, so we have a project that is a device registry stateful service. It's always a good programming practice to separate the actual implementation from its interfaces and domain objects. For that purpose, I will create a separate .NET Core class library. I will follow the same naming convention, and I will name this interfaces. Okay, I went ahead and deleted the default class that was created. And I will go ahead and install the remoting package as well here. And there seems to be a compatibility issue with installation. I know how to fix that. You just have to set the platform to 64-bit for all the projects in the solution. Try again. And that seems to fix the issue. Moving on, the first thing we need is a class to represent the IoT device. So I created a device class. And the device should have a unique ID, which is a GUID, a type, a registered date, and finally a status property. Since this class will be a data transfer object that will be accessible by other services, we need to decorate it with the appropriate attributes, data contract for the class, and data member for the properties. Next, I will add an interface. I will expose the methods implemented by the device registry service. We'll limit iDevice registry, we'll make it public, and the first method will return all the devices. So get devices. Then we need another method to add, or in other words, register a device in the system. And then finally, the third method will return the information for a particular device. Before we proceed any further, this is a good point to discuss the communication options we have with Service Fabric. Out of the box, Service Fabric provides 3 communication protocol options: HTTP, WCF, and service remoting. Since we're developing a system solely with Service Fabric reliable services, the best choice is service remoting. Not only it is the fastest of the 3, it also handles service address resolution and automatic connection retry and error handling. At the time this screencast was recorded, the remoting V2 stack was available. The V2 stack performs even faster, but it requires a few extra steps to set up, which we will cover in detail. One of the requirements for custom object serialization to work in the V2 remoting stack is to provide an implementation of a specific interface called iService Remoting Message Serialization Provider. Since we will be using custom objects to communicate data between services, I will now create a custom data contract provider that implements this interface. Still in the interfaces project, I will add a custom data contract provider class. And this class will implement iService Remoting Message Serialization Provider interface. I will reference the remoting.v2 namespace and bring in the interface methods. Okay, we can see there are 3 methods that I need to provide custom implementation for. First, I will add 2 private fields. One will hold a reference to the serialization provider, and the other is an IEnumerable of the custom data types that need to be serialized for communication purposes. Next, I will add a class constructor, which instantiates the provider and provides an implementation of IEnumerable as a list of types. As you can see, we need to specify both the types of objects as well as the type of the collection of objects. So we have the device type and the list of devices type. Next, I will quickly add some code in the 3 methods and explain. The first method returns a message body factory. The second method concatenates the list of custom types we defined to the request body types of the request serializer. And the third method concatenates the list of custom types to the response serializer. And this is all we need to enable custom type serialization for the V2 remoting stack. I will go ahead and rebuild the solution to make sure everything compiles without errors. Okay, everything looks good. Not that the interface has been created, I will reference that in the device register project, and I can implement it in the device registry class. Okay, another step we need to take in order to enable remoting V2 stack communication is to decorate this class with an assembly attribute. I will bring in the necessary libraries. Okay, good. So now I need to create specific remoting V2 listeners, and for that I will change the code in the create service replica listeners method. This method returns an IEnumerable, and for now we just need to include one listener. And almost there. That's it. As you can see, we're specifying the custom data contract provider that we created a few moments ago. And I realized that the device registry interface needs to implement iService interface in order to use this functionality. Okay, the solution built fine, so everything looks good to go. Okay, we have the device registry class ready, but we still don't have any data to show. For that, I will create an interface, a repository interface, and I will expose methods that will match our device registry class. So get devices, get device and add device. And then I will add a repository class to implement the interface we just created. Make it public and implement the interface. We need a private field that will hold a reference to the iReliable state manager. This is needed in order to be able to create reliable collections and use them as our in-memory data storage. We have that. We will use it in our constructor. And now that we have a reference to the state manager, I can start adding code to the methods that will interact with the data. In the add device method, I will call the get or add async method that will add a device collection to the state manager. And it will add it only if it doesn't exist by checking the name, which I will specify here. Then I will use a state manager transaction. Then I will attempt to add or update a row in the collection. Obviously, the update will happen if a matching key entry exists. Otherwise, it will just add a new one. Finally, I will commit the changes. Okay, that's straightforward. In the getDevice method, I will again access the collection, and then using a transaction, I will try to add the data for that device using the device ID as key. Finally, in the getDevices, I will return a list of all devices. Everything builds. Now switching over to the device registry class, I will add a reference to the repository we just created, and I will use its methods to return data to the callers of this service. Okay, as everywhere else, we are using the async await constructs so that we never block the main thread. Get device, return the data for a specific device. And get devices will return all the devices. All right, cool. Now that we have the repo ready, I will quickly add new code in the run async entry point method to create some data that as soon as the service started will be returned so that we can test if this works. There we go, we're running the application. And using our breakpoint, we can examine the devices collection, and as expected, we can see the 3 devices with all the data properly entered. We will now create an API in order to eventually expose the data to the device monitoring dashboard and also to the IoT devices. All the code can be found at the usual GitHub repo. To create the API, I will add a new project. Under the .NET Core templates, I select stateless ASP.NET Core. The name follows the usual convention. Click OK. And in the next step, I will select the API and click OK. As I did with the other projects, I will update the NuGet packages, and then I will install the remoting package. Okay, then I will add a reference to the device registry interface project and run the solution. Okay, examining the Service Fabric Explorer, we can see that we have one application with 2 services, and those 2 services indeed reflect the device registry and the device registry API. Time to add some code to the API. Let's create a model folder to store our models. And the first model we need is the device. As we did in the registry service, the device model of our API will also have the same properties. ID, type, register date, and status. However, in this case, instead of the data contract attributes, we will use the JSON attributes since this will be accessible through HTTP REST. Now I will add a new controller specifically for the device data. I will add a reference to the device registry using the interfaces project. And in the control constructor, I will create a new service proxy factory specifying the custom data contract provider that we created. Okay, then I will assign this new service proxy to my device registry service field so that I can use it further down in the code. I want to stop here and explain this important piece of code. In order to establish a communication channel from API to the device registry service, we need to know a few things. First, we need the URI of the device registry service, which uses the naming convention, fabric, application name, service name. We also need to specify the partition key and the replica. You must remember from our first screencast about Service Fabric that stateful services, such as the device registry service, can have multiple partitions and replicas. One thing to know is that we should never assume that the Service Fabric service is always running on the same location on the cluster. Service Fabric always shuffles services around nodes and also changes replicas from passive to active as needed. There can only be one active replica at a time, and obviously we need to know which one that is in order to establish communication with it for a given request. Luckily for us, we chose service remoting for intra-service communication protocol. Service remoting provides automatic service address resolution. So for partition key, we will use 0 since we only have one partition in our stateful service. And for the replica, we will just tell the remoting protocol to use the primary replica. Okay, let's continue adding code to the controller. First, I will add a get method that will return a list of devices. This method will return a task of IEnumerable. I will call out to the registry and use the appropriate method, which is get devices. And I return a list of devices ordered by register date. And using the magic of link, I will project each row in the results to the device model in order to return the data in a nice JSON format to the caller. Okay, this is straightforward. We'll decorate with the HTTP get attribute. And to save time, I will paste the code for the rest of the methods here. Here we have the code for the get method for one device and the post method for adding a new device. Now we'll rebuild the solution and make sure we don't have any compilation errors. It's time to test the API and see if our code works. First, I will change the default URL to point to the newly created controller and to the get devices method, and I will run the application. The application runs in the browser and we will see the data appearing in JSON format on the screen. This is the mock data that we added in the device registry. I will do a more thorough test using Postman, which is an excellent tool to manually test APIs. First, we'll call the get devices method and we see the 3 devices. And then I will call the add device, which is a post method. In the body, we can see the new device that I'm adding. and then back again, I'm going to run the get devices and see the newly added device. We can see that the GUID is the default value, and that's okay. The intention is for the IoT devices to register themselves when they come online, and therefore the devices will supply their unique ID to the controller. In this step, we will create the device actor that will act as the device twin and store the telemetry data of its device. Actors are highly scalable single-threaded stateful services and therefore a natural fit for IoT device twins. To add a new Service Fabric service, I right-click on the Service Fabric project and this time select .NET Core Actor service. I will use the usual namespace prefix and name this service Device Actor. Right, this time the template generated two projects, one for the actual actor implementation and one for the interfaces. So that saves us a step. Looking at program.cs, we can see similarities to a console application. There is a main method as the entry point, and as we can see, after registering the service thread is set to run infinitely and wait for incoming requests. Service Fabric, of course, will determine when and if the actor needs to be deactivated, usually after some time of inactivity. When an actor is deactivated, the actor object references are released and garbage collected, but the data associated with the actor is not lost. When the actor comes to life again, its state is restored, which is perfect for IoT devices that can be turned on and off. The device actor class implements iDevice actor and provides some base actor lifecycle implementation. But first, I will update the NuGet packages. Then, I will add a telemetry class, which will be used to represent the device telemetry data. We will need properties for the timestamp, temperature, and humidity. Again, we need to decorate the class with the appropriate serialization attributes. Okay, in the iDevice actor interface, I will remove the default method signatures and add two new ones, save telemetry and get telemetry. And in the device actor class, I will also remove the old methods and implement the new ones we just added. The get telemetry method will return the data stored in the state manager in a device state collection. And that's defined by the name here. The save telemetry method will set the new values in the device state. We are storing only the current values because we do not have a need for the historical telemetry values. If we wanted to, we could have stored them in memory, or we could have saved them in external databases for historical analysis. All right, let's build the solution and make sure everything compiles. Okay, everything looks good. So I will add a new telemetry class in the models folder in the API so that we can use it in the telemetry controller. I will now add a new controller in the API project to expose the telemetry endpoints. First, we need a method to establish API to actor communication. And for that, I will reference the iDevice actor interface. And it looks like we need the appropriate actors package. In NuGet, I'll try to install that. Looks like that failed to install, and it looks like we have an incompatibility with an older package for diagnostics. So I'm going to spend a little time and fix that, and then try again. I have to find the compatible versions. Okay, that took a while, but it looks good now. Back in the code, I will continue developing the telemetry controller code. So the getActor method will establish communication with the actor using the URI. Note that there'll be a slight difference here with the URI naming convention. You will notice that in the name of the actor service, an additional word has been added, the word service. This is important to know if you're having trouble communicating with an actor. Okay, next we will add the get method that will return the telemetry data. This is a public method. There will return the humidity, temperature, and timestamp. Right, and we also need a first let's set the attribute for this, and we also need a post method that will send the new telemetry data to the actor to be saved. So always everything is async so that we do not block the main thread. You can see we're using the getActor private method in both of the API endpoints. And the way we find the appropriate actor is by device ID. Okay, and then the method to save the telemetry. Okay, since we added a bunch of new code, I will run the application and do some testing. Service Fabric Explorer shows no issues. I will navigate to the API URL, and we can see the expected mock data coming from the registry service. Using Postman, I will test the endpoints again. First, we get the devices. Then I will randomly copy the ID of one of the devices and use it in the post telemetry method. Paste the device ID. And as you can see, I have pre-filled the body of the post request with certain telemetry values. I send the request, and then using the getTelemetry endpoint, I will examine the data, making sure I supply the same device ID. We can see that the telemetry data was saved properly, which means our code works, and we are top of the line coders. Let's have a quick recap of what we've done so far. We have developed the device registry that deals with the device metadata, the device actor service that is the device twin and deals with the device telemetry data, and the device API, which is the conduit through which external clients can communicate with our stateful services. Next, we will deal with the telemetry monitoring dashboard and the device simulators. To create the dashboard again, I right-click on the Fabric project and select stateless ASP.NET Core. The name of the website will be dashboard.web. And this time we will select the web application MVC template. First thing is to update the NuGet packages. In order to keep the screencast from being too long, I will be pasting code and explaining what it does. In the index view, I will paste some HTML that sets up the device twin dials in a container of 3 columns. I also added some JavaScript and jQuery code with 2 important methods. One method makes an HTTP call to the API and gets the devices, and then for each device, it calls the getTelemetry method that returns the telemetry data for each device actor, again through the API. In the layout CHTML file, I will include a script reference to a library that I am using for the canvas gauges. These are the dials that show the device telemetry, and you can find examples and downloads in the website that I'm showing here. Inside that CSS, I will increase the screen size in order to fit the 3 gauges in one row. For the website to call the API, we need to enable CORS on the API. This is standard practice whenever there is a need for crossing domains through HTTP. In startup.cs of the API, I just need to add CORS in the list of services registered to the IOC container that comes standard with .NET Core. Then in the HTTP request pipeline configuration, I will specify that CORS needs to be used and open for all origins. In production code, you probably want to be more restrictive and allow only certain endpoints. Let's build the application once again. Okay, since we're ready to work with real data, I will delete the code that populates the device registry with mock data, and I will run the application. And what we will expect to see is the default API method being called and no data coming back. And that's correct. Okay, now we want to browse to the web application that I just added. To get the port that this is running under, we can check the service manifest. And there it is, port 8341. Back on the browser, I will navigate to the root of that port. And we can see that the device telemetry dashboard index page is showing without any dials as expected, since we have not activated any device simulators yet. Okay, the last thing that remains to examine is the code for the device simulators. I will open the Windows Presentation Foundation solution that I developed for the simulators. Again, all this code is at the GitHub repo that I have referenced throughout the screencast. This is a simple application with one view representing a device with 2 sensors. There is one slider to set the temperature and one for the humidity. On the top, there is a placeholder to display the unique ID of the device. The ID of the device is what is used to spin up new instances of device actors, each one having its own state. In the code, we can see that in the main window method, we set the address of the HTTP client to point to the API. Then in window loaded, we call the register device method, which registers a device in the device registry. Further down, we will see that we have methods that set the temperature and the humidity every time each slider is moved on the simulator. The data are passed through the API to the actors, and the expectation is to see the data reflected in real time on the dashboard monitor. It's time for an end-to-end demo. Here on the device telemetry monitor dashboard, as I spin up a few device simulators, we should expect to see the device twins appearing and reflecting the simulator data. To activate a device, I will navigate to the folder where the device simulator executable is, and I will run the first instance. There it is, and a few moments later, you will see the device twin appearing on the dashboard, and you can compare the serial number on the simulator and the device ID, and you can see it matching. And now I will modify the values of the temperature and humidity on the simulator, and you can see that the updated values automatically appear on the dials on the device twin. I will start another instance of the device simulator, and as soon as that starts, a new device twin appears on the dashboard with a matching ID. Now, changing the temperature and humidity on this new simulator updates the corresponding device twin. And we can check and see that each simulator updates its own device twin on the dashboard. So we're going to start a new device simulator, and the digital twin appears soon after. And I'll play around with the values on all three simulators so that we can see that everything works fine and only the corresponding device twin is changed. And there it is. We have successfully built an IoT simulation system powered by Service Fabric. This type of digital twin system can accommodate thousands of devices running simultaneously. I hope you enjoyed this exercise as much as I did. Please do not forget to subscribe to my channel and stay tuned for more interesting Azure related content coming soon. Until then, take care and thanks for watching.